My name is Dr. Vladislav Shteeman. I would like to present you our new research, Analytical Approximation for Photonic Array Modes in two-dimensional photonic devices. The object of the research are electro-optical components of two-dimensional cross-section, including a large number of coupled optical waveguides or phased lasers, so-called two-dimensional photonic crystals. The light is confined in the XY plane of the device and propagates along its optical axis, or Z-axis. Here you see examples of those photonic devices: 2D array of coupled waveguides and 2D phased laser array. The researchers. The research was conducted by me, Dr. Vladislav Shteeman. I am with the Electrical Engineering Department of Brody College, Carmel, Israel. Professor Amos from the Electrical Engineering Physical Electronics Department of Tel Aviv University, Tel Aviv, Israel. And our students, Elena Smith from the Electrical Engineering Physical Electronics Department of Tel Aviv University and Electrical Engineering Department of Brody College, and Edor Gil-Adi from the Electrical Engineering Department of Brody College. The purpose of the research was develop a full analytical description of array modes, electromagnetic fields and propagation constants for two-dimensional photonic crystals, namely devices containing a large number of coupled waveguides or lasers, in which light is confined in XY plane and propagates along the optical axis or Z-axis of the device. The description should cover both photonic lattices and superlattices. Here you see example of 2D photonic lattice or periodic array of identical waveguides or lasers, and 2D photonic superlattice, periodic sequence of groups of different waveguides or lasers. Theoretical background: coupled mode theory. Let me start from the modes expansion conjecture. Consider a general case of a superlattice, namely array of ny by nx identical groups, so-called supercells, where a supercell is a group of sy by sx different waveguides. In the particular case of sy equals to sx equals to 1, superlattice reduces to a lattice or array of identical waveguides. Array modes or guided modes of the array can be represented in the following way. Transverse component of array mode propagating along Z-axis is a linear combination of transverse components of all guided modes of all solitary waveguides, multiplied each by its partial amplitude, and all this linear combination multiplied by the running exponent e in power I sigma z, where sigma is the propagation constant of the array mode. Let me show you the example of array mode. Consider array of 11 by 11 identical single mode waveguides. In this case, nx equals to ny equals to 11, sx equals to sy equals to 1. Guided modes of all solitary waveguides and their corresponding propagation constants are known in advance. We are to find a envelope function, or a set of partial amplitudes, and b propagation constant of the array mode. If we find this, we can reconstruct the full array mode with the mode's expansion conjecture shown on the previous slide. Standard coupled mode approach for finite arrays. For computation of a full set of envelopes U0 and propagation constants sigma, one should solve coupled mode equation matrix M, coupling matrix times U0 equals to sigma propagation constant times U0. Computation of array modes. In order to reconstruct the full set of array modes supported by the device on the basis of the mode's expansion conjecture, it is necessary to compute the full set of envelopes U0 of the array modes and their associated propagation constants. We can do it in two ways. One way is to follow the standard coupled mode approach, namely solve coupled mode eigenequation for U0 and sigma. Another way is analytical approximation. We are going to discuss here. For arrays containing a large number of unit cells, namely solitary waveguides for lattices or supercells for superlattices, find U0 and sigma analytically without computation of coupling matrix and subsequent solution of coupled mode eigenequation. Analytical approximation. Main idea of the analytical approximation. There are basic assumptions we want to start from. Since the leak of the model fields outside the photonic array is negligible, two-dimensional array of identical unit cells, namely waveguides for a lattice or supercells for a superlattice, can be roughly approximated by an auxiliary waveguide, a hollow core metallic waveguide. Next, for large 2D photonic arrays containing a large number of unit cells, the full set of envelopes U0 can be approximated on the basis of guided modes of this auxiliary waveguide, discretized at the centers of the unit cells. The full set of propagation constants sigma can be computed using guided modes of the auxiliary waveguides and extended coupled mode formalism for infinite arrays. Here you see the example of rectangular superlattice, its supercell, and auxiliary rectangular metallic waveguide, which can be used in the approximation. Here you see hexagonal superlattice, its supercell, and auxiliary hexagonal metallic waveguide, which will be used for the approximation as well. First, analytical evaluation of a set of envelopes U0 with guided modes of an auxiliary metallic hollow core waveguide or standing waves of a 2D membrane. Here you see three first guided modes of a square metallic hollow core waveguide used in approximation for 2D square lattices and superlattices. Analytical solution for model fields in form of sinus kx x times sinus ky y is available. The dominant spatial frequencies of the fields are kx and ky correspondingly. Here you see three first guided modes of a hexagonal metallic hollow waveguide used in approximation for 2D hexagonal lattices and superlattices. fast numerical solution for model fields is available. The dominant spatial frequencies of the fields, namely kx and ky, can be found with Fourier transform procedure, FFT. If the original photonic array contains n total unit cells, waveguides for lattices or supercells for superlattices, we need n total guided modes of the auxiliary metallic waveguide, or n total standing waves, and n total different pairs of dominant spatial frequencies, kx, ky, for the approximation. Second, analytical evaluation of the full set of propagation constants sigma. There is so-called extended coupled mode theory, extension of a standard coupled mode theory to the case of infinite photonic lattices and superlattices. It is actually a combination of coupled mode formalism and plane wave expansion approach. Extended coupled mode implies periodic boundary conditions and assumes in advance that the envelopes of the array modes U0 are plane waves. In the computations, extended coupled mode theory only accounts for coupling between the waveguides in a single unit cell, positioned at the center of infinity, with their neighbor waveguides, located both inside and outside the central unit cell. It does not account for coupling between all waveguides in the array, as it is in the standard coupled mode theory. For this reason, the approach is very fast. The computations require 10 seconds on a standard PC machine. As an input parameter, extended coupled mode theory requires pairs of dominant spatial frequencies kx, ky of the plane waves U0, or wave vectors kx, ky from the first Brillouin zone of the corresponding 2D photonic lattice or superlattice. This allows accurate analytical evaluation of propagation constant sigma and automatically photonic band structure sigma versus kx and ky. Nevertheless, this approach does not allow accurate evaluation of envelopes U0 and therefore total fields of an infinite photonic array. For computation of propagation constants sigma, extended coupled mode theory solves parametric eigenequation with wave vectors kx and ky from the first Brillouin zone of the corresponding 2D photonic lattice or superlattice as the parameters, namely matrix M double underlined as a function of kx and ky times its eigenvector U0 double underlined equals to propagation constant of the array mode sigma, being an eigenvalue of M double underlined. Sigma is kx, ky dependent, times the same eigenvector U0 double underlined. Assume that we computed a set of n total guided modes of an auxiliary metallic waveguide and n total different pairs of dominant spatial frequencies kx, ky. Branch number 1. Discretize n total guided modes of the auxiliary waveguide at the centers of the unit cells. This yields us a full set of envelopes of array modes U0. Branch number 2. Use the kx, ky pairs of the incoming parameters for the extended coupled mode theory for infinite arrays. This yields us a full set of propagation constants of array modes sigma. Array modes can be reconstructed with the modes expansion conjecture. Photonic band structure sigma versus kx and ky is received automatically with the extended coupled mode theory for infinite arrays. Note, Since there are two independent methods for computation of U0 and sigma, computation error in the calculation of U0 does not affect the computation error in the calculation of sigma. The advantages of the approach. The approach is very fast. Computation of optical characteristics, array modes and photonic band structure of large 2D photonic crystals, including a large number of coupled elements, lasers or waveguides, become available on the timescale of a few hundreds of seconds on a standard PC machine. The computation time is virtually independent on the number of elements in the array. The approach is very accurate. For the first time, analytical prediction of model fields and their associated propagation constants in 2D photonic lattices and superlattices become available. The benchmark. As a benchmark, we used well-known Helmholtz equation, namely a second derivative of the array mode field by x and y plus k0 square and square times array mode field equals to sigma square times array mode field, where sigma is a propagation constant of the array mode and a e is a transverse component of the array mode field are unknown, while k0, which is equal to 2 pi over lambda 0, and lambda 0 is the injected wavelengths, and n, the whole photonic array refraction index distribution, are known in advance. Results and discussion. As a first example, let me show you array of 217 identical waveguides arranged in hexagonal lattice. Here you see the parameters of the lattice. And this is a unit cell of the lattice. This is actually a solitary waveguide. This graph presents effective mode index of the array modes of this photonic array, where effective mode index is sigma over 2 pi over lambda 0. The effective indexes were computed by Helmholtz equation, standard CMT, and analytical approximation. Note a close agreement of the results acquired by the three methods. Here you see spatial distribution and n effective of the first array mode of the first photonic band of the hexagonal photonic lattice, computed with the analytical approximation, standard CMT, and Helmholtz equation. As a second example, let me show you analysis of 2D photonic superlattice, where a supercell, a unit cell of the array, contains 4 waveguides of 2 different types. Here you see the parameters of the photonic superlattice. On this graph you see effective mode index sigma over 2 pi over lambda 0 of the first, second, third and fourth photonic bands as computed with Helmholtz, standard CMT and analytical approximation. Note again close agreement between the results acquired with the three different methods. Here you see spatial distribution and an effective of the first array mode of the first photonic band of the square superlattice, computed with the analytical approximation, standard CMT, and Helmholtz equation. Note again the close agreement between the results. As you just see, our new analytical approximation is accurate. But in addition to high accuracy, this method is very fast. In our computations, we used a standard PC machine with Intel Core i7 CPU and 8 GB RAM. The machine time required for the calculations of propagation constants and model fields of the array modes with the analytical approximation was about 150 seconds for the square superlattice and about 200 seconds for the hexagonal lattice. Same calculations with the standard CMT required 30 minutes for the square superlattice and 50 minutes for the hexagonal lattice. Solution of the Helmholtz equation in finite differences required 10 hours for the square superlattice and 24 hours for the hexagonal lattice. Conclusions. For the first time, analytical expressions for photonic array modes in 2D photonic crystals, photonic lattices and superlattices become available. The analytical approximation allows very fast, a few hundreds of seconds, and accurate computation of array modes in photonic devices containing a large number of coupled elements, lasers or waveguides. The computation time is virtually independent on the number of elements in the array and almost does not increase with increasing the latter. The analytical approximation allows deeper insight on the influence of different parameters of a photonic device, such as core-clad contrast, geometry of a solitary waveguide, photonic lattice symmetry, and so on the array modes. Here you see a list of references for this research. Here you see a list of references for the related research, analytical approximation for one-dimensional photonic lattices and superlattices. Thank you for your attention.